ways in which we can help will create substance the ways by which we live.
Welcome to another interview on energynews.biz. My name is Adnes Biogradlia and my guest today is Alain Prinzhofer, an eminent figure in the world of geochemistry. His expertise as the Scientific Director of GEO4U and contributions to natural hydrogen research have significantly advanced our pursuit of clean and renewable energy sources, earning him a place at the forefront of energy innovation. Alain, welcome.
Thank you very much, Alain, and thank you for your invitation.
Can you tell me who is Alain Prinzhofer?
Well, that's quite a general question. I'll try to focus rapidly. I'm a researcher, I'm a geologist, a geochemist, as you said, and I worked in both the academic world and the applied research during all my life in a lot of fields. And these last years, I am mainly devoted my work on natural hydrogen knowledge and exploration.
Throughout your distinguished career, what initially drew you to the field of the gas geochemistry, and how has your focus evolved?
I would say that I started a long time ago now when I entered the IFPEN in France, the French Oil Research Institute, and I launched at that time a new project on natural gas, which at that time meant mainly hydrocarbon gas, methane, ethane, propane, etc. And it was a time when natural gas hydrocarbons were not so interesting. People were looking for oil and not for gas. But as you know, things were changing, and now natural gas like methane is quite important in our energy budget. So I started to work on other natural gases, hydrocarbons. Then I worked on non-hydrocarbon gases, CO2, of course, storage, etc. And at the same time, I was always curious about some papers which were speaking about natural hydrogen, which was absolutely not known at that time. A lot of people claimed natural hydrogen doesn't exist on Earth. And I knew it did exist because there were some forgotten papers about that, but it excited my curiosity. And that how the story started, I would say 15, almost 20 years ago. I was just curious about this exotic gas, which was presented in some papers which were forgotten then. And I began to be trying to work on natural hydrogen. Still at that time, it was in France, in the French Oil Research Institute.
The Marcia project in Brazil signifies a breakthrough in hydrogen exploration. What inspired you to investigate this area for natural hydrogen?
Before starting in Brazil, as I told you, I was looking for hydrogen in a lot of places on Earth. And we realized with some colleagues at that time from IFP that natural hydrogen was quite common in almost any continent. It started in geological formations called ophiolites. I worked in Oman Sultanate, in Philippines, New Caledonia, etc. And we met some Russian colleagues showing us that there was also some natural hydrogen in the middle of the continents. And from that time, we began to visit a lot of places, and we noticed that all the old continents, Eurasia, Australia, Africa, South and North America, are indeed quite rich in this new energy resource, natural hydrogen. So, and for other reasons, I had the opportunity to live in Brazil and to work in Brazil, and I was looking for natural hydrogen in Brazil. I discovered that in a lot of places, I would say almost any place I was looking for in Brazil, we found natural hydrogen evidence.
Could you elaborate on the technological advancements in detecting and quantifying natural hydrogen in geological formations?
Yeah, that, I would say that it started really almost from scratch. Almost measuring hydrogen detectors in the field was something which was very difficult to find. And today, of course, the situation has changed, and we have a lot of options to get some hydrogen detection directly on the field. Generally, this exploration starts with something which I call superficial. We are doing superficial geology, meaning you are going on the field or you are using some geological maps or satellite photos, and you try to get some information about hydrogen seeping out of the subsurface, just at the surface, because it's simpler. When you get this information, you say, okay, there is a subject there is hydrogen seeping out in this area. Then you begin to do some subsurface studies like geophysics, etc. And you continue and you end more or less with the real judge of the story, which is a well. You drill 1, 2, 3 wells, and you confirm or not, of course, that you have hydrogen. I would say that this is the technical part. Apart from the technical part, there is a scientific part. When we began to work on natural hydrogen, mainly in continental areas, nobody knew anything about the genesis of hydrogen. How is it formed? Nobody knew. How does it migrate? Nobody knew. Does it accumulate like a usual hydrocarbon accumulation, or is it a different kind of accumulation? Nobody knew. So there is a huge scientific research work which is done now with a lot of research centers, academic or not, in order to try to understand a little bit better what we call now a hydrogen system, in analogy with petroleum systems, with a source, migration, accumulation, leakage, alteration, etc. So all this work was initiated several years ago, I would say marginally, and in the last 3-4 years, it's absolutely not marginal, as you are aware of. Both the research on nitrogen hydrogen is increasing everywhere, with a number of scientific papers appearing every week, which is exponentially increasing. And also on the business part, a lot of first startup companies, then bigger companies, now major energy companies are now working on this new resource. But this is quite recent, meaning that the knowledge we have of this field is still extremely small. We need a lot more information to consider that we are really controlling exploration and future production of natural hydrogen.
How do you foresee natural hydrogen's role in a global energy mix over the next few decades?
Well, that's something which is, of course, difficult to elaborate in a scientific way. Let's put it in a way which is a little bit more modest. Today, we know that first, natural hydrogen does exist. It's clear. Nobody claims that it's just a dream. It doesn't exist. We know that in several places on Earth, it is producible. As you know, in Mali, the company Hydromar was really pioneering the exploration and production of hydrogen. Now Australia is really giving its gold rush for hydrogen with some wells that have been drilled recently, etc. So there is no question that it has an industrial and sociological impact. How much? Difficult to know. It appears that hydrogen is present, I said, almost everywhere. And is it producible everywhere? Nobody knows. It appears also that in a lot of cases, natural hydrogen is renewable at human time scale, meaning when you produce it during 10 years, 15 years, this was seen in Mali, you know that there is a refill of your accumulation. So, of course, hydrogen is clean. When you burn it, it gives only water. It is renewable. It is appearing almost everywhere on Earth, but we don't know yet how it is producible. It means economically at what price. From the examples we have now, the price of production of natural hydrogen is between 0.5 and $1 the kilogram of hydrogen. This is perfect. It is much, much cheaper than any manufactured hydrogen, and it's more or less the same range of money than hydrocarbons in terms of amount of energy. So fair enough. Will it be possible to produce everywhere where we find hydrogen with such a price? I cannot answer. This is too early to say. But so to summarize the answer to your question, we know that natural hydrogen will be a part of our future energy mix, for sure. In what proportion and in what competitive way, it's very too early to say.
In your recent work in Marcia, you have indicated a new paradigm in hydrogen exploration. Could you explain the key findings that led to this conclusion?
Well, what we have seen recently, and that's the last paper I published, is that in a city very close to Rio de Janeiro in Brazil, we have again superficial evidence that a hydrogen system is functioning, and we don't have more evidence so far because it's just, as I said, the first step of the work, which is the superficial step. We will need more in-depth studies to know how it is accumulating or not, in what amount in the subsurface. But we know that there is clearly a subject about hydrogen seeping out in the atmosphere. Moreover, we have seen that associated with this hydrogen seeping out, we can measure also some helium. We knew already that very often when you have deeper accumulations of hydrogen, very often helium is also a kind of byproduct of hydrogen. And as you know, the market of helium is extremely tense, and discovering new helium reserves, it's extremely important. The news about this work we have done is that helium is even visible in the soils, meaning with the hydrogen seeping out, we find associated helium in the soil at like something like 80 centimeters of depth, which is really something new. This has several consequences. First, when you measure hydrogen in soil, some people claim that maybe it's an artifact, or it may be related to the way you drill the soil and you generate hydrogen, or it may be a superficial biological hydrogen, etc. When you have associated helium, it's not possible. Helium has to come from deep. It cannot be generated and staying in the soils. So we are dealing with a new way to prove the existence of hydrogen system using helium as a proxy for hydrogen systems, but also as helium as an economical interest indeed. The association of hydrogen and helium already in the soils indicates that there is probably an interesting potential if we find an accumulation in the subsurface where we can produce both hydrogen and helium. Just to give you some economic information, the price of helium is more or less 100 times the price of hydrogen. Meaning if you find a gas accumulation which has, let's say, 80% hydrogen and 2% of helium, considering the price of helium, what you have, economically speaking, is mainly a helium accumulation, because the amount of money related to helium will be bigger than the amount of money related to hydrogen if you produce it. You have, of course, geologically speaking, a hydrogen accumulation with a little bit of helium, but economically speaking, you have a helium accumulation with some hydrogen as a byproduct economically. So helium is a byproduct geologically, and hydrogen is a byproduct economically.
With technological advancements, what future research methodologies do you find promising for exploring natural hydrogen?
Well, we're working with a lot of new methodologies that we're testing. For example, and this is unpredictable. A couple of years ago, we discovered that a technology called gamma spectrometry, meaning you measure the radioactivity of uranium, thorium, and potassium, the natural radioactivity, at the molecular level of the soils with some instruments, and you can do some mapping of that. And we have seen that this is an excellent proxy for hydrogen, mainly thorium concentrations in the soils. This is new, and it's a new methodology that we're using now. I would not say in tech service, but almost, because it is appearing like that. We are discovering that a technique called INSAR, which is a radar interferometry of measuring the movement of the continents with a precision of millimeters per year, something extremely precise. When you have hydrogen functioning, you have a movement of the rocks, which is probably related to the fluid movements of the subsurface. This is a new proxy. In terms of geophysics, we know that for oil and gas exploration, people are using mainly what is called seismic reflection, and you can get a geometry of the subsurface. Of course, it will be useful for hydrogen, but we add some new methodologies like passive seismic, seismic refraction. I won't comment all these techniques, but they are under test. What we know is that probably some of these tools will be extremely useful, some of them will be less useful. But you know, in natural science, you always need to cross a lot of perpendicular tools in order to get the best information. The best information is reducing the risk when you will really invest your money drilling some wells to get your accumulation. So we are really on the process of, I would say, every 2-3 months, discovering and testing a new methodology in order to ameliorate hydrogen exploration. But again, this is something which is really new, and we will see in the future, in the coming years, what are the tools which are paramount and what are the tools which are okay but not so interesting than the other ones.
How do you assess the commercial viability of natural hydrogen as an energy source based on the current exploration technologies?
Well, first, as I said, the first point is that the price estimated for hydrogen, for natural hydrogen, is much smaller. I said between 0.5 $1 the kilogram of hydrogen. As you are aware of, what is called gray hydrogen, meaning hydrogen generated from carbon sources, and you generate 1 kilogram of hydrogen and you generate 12 kilograms of CO2. The cost is $2-3, so it's already more. If you try to get virtuous hydrogen, which is called green hydrogen, through electrolysis of renewable electricity, the price is, according to the price of electricity, between $5 and $12 a kilogram. It is absolutely huge. It's extremely difficult to imagine a business in the future with such a price. And in fact, today, everybody speaks about green hydrogen, but when you look at the real data on Earth, the proportion of green hydrogen in the hydrogen production is 0.04% of the total hydrogen generation. It's completely marginal, just because it's too expensive. It's virtuous, but too expensive. So the natural hydrogen arrives with a price which is in accordance with the usual price of energy today. So that's really the very positive point. There are two negative points, I would say. The first one is that natural hydrogen is never 100% H2. You have always some other gases. I spoke about helium, but you may have nitrogen, you have methane, diluting your hydrogen. And according to what you want to do with your hydrogen, you need to purify your hydrogen or not. It depends. The second problem is that producing hydrogen or generating hydrogen, we know how to do. We know very well how to do transportation of hydrogen, but it has a cost. It's quite expensive. And generally, people consider that it's better to have the hydrogen source close to the hydrogen consumption. If you find hydrogen in the middle of nowhere, natural hydrogen, and you want to use it in a big city, which is 500 or 1,000 kilometers from there, you need a lot of investments. So when you build a hydrogen plant to generate hydrogen, well, you can decide, oh, I will put my plant next to the city. When you find a hydrogen system, you don't choose. It's nature which chooses for you. And in this case, you need to find places which are relatively close to the areas of consumption so that you don't increase the price of your hydrogen because of the transportation. So there are parameters which are, of course, important now. We are quite optimistic because, as I said, it seems that hydrogen occurs in almost anywhere in continents where you begin to look for it. So it would be probably possible to get hydrogen accumulations, producible accumulations, close to the areas of consumptions. But once again, I cannot claim we are sure about that. It has to be tested in the future.
How do you ensure that the hydrogen flux measurements aren't affected by external contamination?
You mean what kind of contamination? I'm sure I don't understand. You have hydrogen flux, that natural hydrogen flux that we measure. You're dealing with what kind of contamination? I mean, human contamination
During the measurements, can there be any contamination?
Contamination, no. Maybe if you were really measuring hydrogen above hydrogen plants, but that's not the case. In geology, we go in places which are relatively salvage. And the only contamination we may have when we measure hydrogen, as I said, are artifacts which may be either due to human activities like drilling. You drill, and it's a very well-known process. When you drill with a bit which is metallic, if the temperature increases, if you have water, you have a chemical reaction between the drill bit and water, and you generate artificial hydrogen, which has nothing to do with what we are looking for, of course. This is something which has to be tested, and you may have a doubt about your measurements because of that. As I said, for example, association with helium is a good way to avoid this kind of problem. People consider also that possibly in the soils you may have biological hydrogen generation. This is not clear in the scientific world because biologists consider more that the soil is a hydrogen sink rather than a hydrogen source. So, and the biology which does exist in soils needs hydrogen, and it's consuming hydrogen, and sometimes it's consuming hydrogen from the atmosphere. You have concentrations of hydrogen in the air which is extremely small, something like 0.5 parts per million. It's extremely small. But this very small proportion of hydrogen is pumped away by the biology of the soils because they need this hydrogen as a source of energy, exactly like us. Hydrogen is a source of energy, first for biology. And human beings are arriving now discovering that, but bugs discovered nitrogen as a source of energy, I would say 3.5 or 4 billion years ago. We are a little bit slow.
With no documented hydrogen-prone formations in Marcia rocks, what suggests the presence of significant hydrogen and helium fluxes?
In terms of generation of hydrogen, there are a lot of works which are being done now. I would say that 15 years ago, 10 years ago, we had only one possibility imagined by geologists to generate hydrogen in geology, which was called serpentinization, alteration of some rocks from the oceanic crust. Today, we have much more possibilities for hydrogen generation, which are well documented. If I try to classify them, the main process considered today for hydrogen generation is what we call chemically water reduction. Water is H2O, and if you reduce, which is the contrary of oxidation, you reduce your water, you get H2, which is natural hydrogen. And the reducer, the most common reducer on Earth is iron. You have iron is, of course, a very common element on Earth, and iron may be acting like a reducer of water. And this is probably the main process. But you may have other reducers. Sulfur, which is also quite abundant on Earth, may be a reducer for that. So there are other processes which can generate hydrogen. We don't know yet what is the relative importance of each of these processes which have been described and published. Each of them are possible. People are considering that radiolysis may be also a process. Radiolysis is the breaking of water molecules through natural radioactivity in rocks. It breaks the H2O molecule, gives H2 and molecules with oxygen. It's also a process which does exist. What is the importance of this process compared to water reduction? Nobody knows. And possibly one process may be a catalyst for another process to generate reducing conditions in the area where you have your kitchen of generation, and then another process will be more efficient thanks to a first process. All these considerations are still research for the moment. And as I say always, we are today in the same situation than 1 century or more than 1 century ago, considering petroleum. At that time, nobody understood really the generation of petroleum. But it's not because we didn't know the generation of petroleum that people were not able to find petroleum accumulations in United States, in the Caspian Sea, in the Middle East. And as you know, a lot of fortunes were done with that before people understood what is the real generation of petroleum linked to organic matter. This occurred in 1930s only, but much before that, you had a lot of oil production. Hopefully, for hydrogen, we are a little bit better, and the interpretations we have today won't appear to be completely silly in 10 or 20 years. I hope so. But we have to be extremely modest. At the time of the beginning of hydrocarbon exploration and production, we had big scientists, chemists like Mendeleev, Berthelot. They tried to understand the origin of oil, and they were completely wrong. So today, I tell you what we think about the generation of hydrogen. Let's be modest and to see what the future will confirm or not about our interpretations today about hydrogen generation. But it's not so important in terms of either business or energy transition where natural hydrogen may play a role. It is not the main point. The main point is, like for oil 1 century ago, finding producible accumulations. The rest is a matter of scientists in order to go further and to discover more accumulations later.
What advances in analytical techniques are needed to improve the detection of low concentration gases?
I would say in labs, you have everything you need. But very often you need to work directly on the field. That's the work of the geologists. And transposition of some analytical techniques, which are very well done in laboratories, where you have air conditioning, controlling of humidity, of temperature, etc. Trying to do that directly in the field, where it may be extremely hot, extremely humid, rainy, etc. And also you need to carry the material. You won't carry 3 tons of material when you are walking somewhere. So this has really the miniaturization of these technologies, and the fact that they would be resistant to the natural conditions is something very important. For example, everyone consider that it's very important to do what you would call hydrogen monitoring. You put a permanent detector in the soil, you let it work during 1 to 3 months, and you record what is the variation of the hydrogen flow during these months. It seems very simple. It's not. There are a lot of problems, technical problems, to consider that this permanent detector won't have flows during its functioning. So this kind of work is done now with a lot of people in a lot of labs, but we need clearly some amelioration of technologies which do exist already. As I said, in terms of geophysics, we need to test some new tools, not so new. There are tools which do exist and which were used for other fields of research. But adaptation to exploration of natural hydrogen has to be done.
How might the hydrogen flux vary within Marcia, and what does this mean for commercial extraction?
The flow of hydrogen directly from the soil to the air, we have done that in some areas in Brazil, in areas called furry circles. There are circular depressions where you have hydrogen flux, and we see that it's extremely variable with time. And in areas like Marika, we don't know yet because we didn't do this monitoring. We have a different geological setting, which is mainly associated with big faults which have been reactivated. It's different from what I call these fairy circles. The general flow in terms of future production is not exactly the same issue. The variation of the very superficial flow of hydrogen is linked to very superficial parameters. Variation of atmospheric pressure, temperature, soil humidity, etc. This has nothing to do with the deep flow of hydrogen, which will fill up your accumulation and possibly refill your accumulation when you are producing. That what we have with the surface measurement is just a kind of average flow of the deep hydrogen system, which has been fluctuating in the soils because of superficial parameters. But the important parameter is not the variation of this flow at the surface. The important parameter is the average flow, which is corresponding to the real one filling up your accumulation.
What are the next steps in researching natural hydrogen as an energy resource following your findings in Marcia?
There are a lot of things to be done in terms of research. As I said, the hydrogen system, we know that there is what we call a kitchen of generation, which is very deep, several kilometers. You have migration. Hydrogen is a very small molecule which migrates very easily in rocks. It may be the porosity of the rocks, it may be through fractured areas of the rocks because of natural faults, etc. It may accumulate, it may be altered. It's a very reactive molecule, also chemically and biologically speaking, and it leaks finally to the air. Each of these parameters or processes have to be studied and quantified in a better way. As I said, generation, we have already a set of a lot of possible processes of generation. What is their relative importance? We don't know. Migration of hydrogen, is it in deep horizons? It is in solution in water, or is it migrating as a gas phase? Good question. We need to work on that, doing some modeling. Accumulations, do we need to have a good seal to accumulate hydrogen? And people claim that, say, well, we need a seal for hydrocarbons, but for hydrogen, we need a better seal because hydrogen is so small, it will leak more easily, and we will miss the accumulations. Some other people will claim, no, it doesn't matter. We don't need a real seal because as it's a constant flux, which is quite important, that's why it's renewable. The only thing we need is a kind of restriction of the flow, what we call a bottleneck. And then you have an accumulation below this bottleneck, exactly like the image I take always is a traffic jam. When you are a freeway, the cars are flowing. If you have a restriction because there is an accident, the cars continue to pass, but you have an accumulation. It's a traffic jam. It may be the same for hydrogen. And in this case, you don't need a real seal. You need just a restriction in the permeability of the rocks in a given area. Is it true? Or is it feasible? All these things that we're suggesting as researchers have to be proven. And I am absolutely convinced that, of course, all of us researchers are working on trying to work with our brain to better understand that. But the real constraints will come from the future production of hydrogen through industrial companies. When you will begin really to have more experience, what happens when you begin to produce hydrogen, you drill, you have hydrogen which is produced and sold, and you see what is the evolution of the pressure, of the composition of the gas in the accumulation. These data will give us paramount information to continue to try to work with our brain to understand better these processes. So the link between industry and scientists is always very important, of course. But in the case of natural hydrogen, I think it is absolutely paramount.
In general, how do you see the hydrogen future? Natural hydrogen, any hydrogen, clean hydrogen, green hydrogen. How do you see this hydrogen economy in the future? Thriving with its shortcomings or being just a hype?
As I say, manufactured hydrogen, if it's clean, meaning green hydrogen, made with renewable electricity and electrolysis, it's extremely expensive, too expensive. And people claim that, well, look, solar energy at the beginning it was expensive. Now the price of the solar panels is decreasing and it's not so expensive. True. But when you look at the real price of green hydrogen, I think 2/3 of the price is the price of electricity, and 1/3 is investments and material, etc. So in order to reduce this price from what I said, $5, $12 to $1, you would need to reduce the price of electricity of a factor, I don't know exactly, a factor 5, something like that. I don't think this is how we feel our future. I don't think that electricity price will be divided by 5 in the coming years. So I'm relatively anxious about the future of green hydrogen because of this extremely high price. And I don't see how you can reduce this price, except saying, well, we don't care. We are producing electricity and we will consider economically that the price of electricity is zero. It's just because we are not used to this electricity. Okay, in this case, you can consider that it's feasible. But with a normal economical model, the price of electricity would kill the project of green hydrogen. Gray hydrogen is cheaper, but as you know, to produce gray hydrogen, you need to use another source of energy, which is hydrocarbon or coal, which is extremely polluting. It's just a change of hydrogen from one form, carbon energy, into another form of energy, hydrogen. And of course, the efficiency of the transformation is below 100%. Makes sense. It's usually 60%, something like that. So you're losing a part of your primary energy, and you are polluting because of this primary energy, which is polluting. So this is another problem, which is not economical, but which is environmental. Does it make sense to change a primary source of energy with carbon into hydrogen, which is clean, considering that you have this CO2 emission? Of course, you can store it, but it increases the price. So I think, but that's just my personal feeling, that natural hydrogen may help to consider the future of hydrogen energy feasible. It's not in opposition with manufactured hydrogen. It is just a price reducer, I would say. If we are right, if natural hydrogen is between 0.5 and $1 the kilo, and you mix it with green hydrogen, for example. Then you reduce the price of the mixture. And even if we don't have enough natural hydrogen to say, okay, now we don't worry with other sources of hydrogen, we have enough to feed the humanity. I don't think so. It won't be the case, but it may help the whole hydrogen business. You just giving a kind of mixture of green hydrogen, which is virtuous, very clean, but very expensive, and you can produce it according to the amount of electricity you are producing. And natural hydrogen, which is controlled by nature, which is extremely cheap, but which has to be produced in some areas. This would give a kind of, it's not an energy mix, it's a hydrogen mix. Hydrogen mix, which would allow to enter into the energy mix in terms of economic viability.
Alain, thank you for this enlightening session. Thank you for being my guest today.
Thank you very much. You're welcome.